class. That was kind of my trailer for the second hour to make everybody stay. So here, we've got.
You're saying watching your videos is like watching the session a second time.
Yeah.
It all makes sense.
Now you're just kissing up.
I know.
Actually, I was having that discussion with a student earlier today about statistics. You know, struggling to take a statistics class and understand it. I did the statistics and I did very well, but I didn't understand why I was doing it until my third statistics class I took. So, I mean, there's a lot of this stuff that you can understand how to do it, but the really reasons why is when you see it the third or fourth time that it really starts to click.
Yeah.
If I had my way, I'd assign you the videos to watch the videos the semester before you take the class, so you're ready to step in and really understand it. We'll see how that works, huh? Oh, sure. So Tim right now is at 26. We're going to retire at 66 and live till 86. So that gives us 40 years here and 20 years here. Rates, we're looking at 9.8% and 4.2%. The big elephant in the room, though, is at 40 years old, Tim wants to take out $140,000. We also know that Tim wants to draw $4,500 a month in retirement. So for right now, it's this liquidation side that we have the third piece of information. So let's go ahead and work with that and figure out what this present value on the liquidation side has to be. I'm going to let you guys figure this out and tell me what it is. I'm just writing out the formula, but I'll let you guys punch it in. Somebody yell it out when they get that present value. Somebody be brave. Okay.
$729,843.26.
27?
27. Oh yeah, 27.
Yep, perfect. So there we go. That's how much that Tim needs to have at retirement in order to pay for that $4,500 a month while Tim is retired. The problem is here, that is not going to be the future value of his retirement fund here. Why not? Well, because this $140,000 being drawn out for a house messes things up. Tim will have that $729,000 at the age 66, but he needs to shoot for more than that so he can cover that extra $140,000. How do we know how much more? Well, it's a lot simpler than it looks. We need to figure out this $140,000 at age 40, what that would have been worth if it had sat there from 40 until 66, all the way up to there. Does that make sense? So that the future value of that 140,000 will be the 140,000 times, now this is just a compound interest problem, 1 plus 0.098 divided by 12, because it's compounded monthly, to the power of 40 to 66 is 26 years, times 12 is what, 314, something like that? Somebody help me out. 312? 312. So, 140,000 times 1 plus point, that should be 0.098. 26 years times 12 months in a year. So that is taking out $1,779,9071. So what that's saying is we need to increase this amount by 1.77 million to account for that 140,000 they took out. Yeah, I know that 140,000 is more than what their retirement is. They could have tripled their retirement if they hadn't bought a house. So we're going to add these two amounts. Adding those two amounts, at 2,500,833.98. Does that look right? Perfect. So that becomes the future value of the accumulation phase. So we're going to use that to find the monthly payment. 2,500,833.98 divided by 1 plus 0.098 divided by 12. Now this is not going to be 312 anymore. It's going to be 40 years times 12. 480 minus 1, close, divided by, open, 0.098 divided by 12, time, that's it, right? Which is the accumulation phase. So, 2,500,833.98 divided by 1, 2, 3. 1 plus 0.098 divided by 12. Close, power of 480. Minus 1, close, divided by open. We get $420.20 a month. Case closed, right? No. Why not? But wait, there's more. We have to make sure there is a chance, even though the numbers work out, that $420 a month would give the required $2.5 million at age 66. We need to verify that it would give the required $140,000 at age 40. So we need to make sure that $420 a month is going to give us a future value of at least $140,000 at age 40. So 420.20 times 123 1 plus 0.098 divided by 12 to the power of, we're going from 26 to 40, which is 14 years, which is what? 168 months, I believe. We're taking their payment here and figuring out what that future value would be at age 40. That is from age 26 to age 40. No, this would be an extra credit question.
Scroll down.
If it's 40 years, it's...
No, from 26 to 40 is 14 years. So then this will be divided by the 0.098 divided by 12. I always like that look of utter fear in the eyes. Is this going to be on the test? Sorry. Yeah. Not even I am that cruel, but these are good ones to know. 420.20 times 123. $150,310.79. So the good news is this will work for Tim, but Tim is going to save from 26 to 40, and at 40 he's going to draw out that $140,000. There's only going to be $10,000 left in there at 40 years old. So basically he's wiping out everything he's done from 26 to 40 and starting over for his retirement. The house is paid off, yeah. So, like I said, it's if you can afford that $420 a month from 26 to 40, then that $400 a month should be easy to afford from there on because you don't have a house payment or rent payment. Okay, now there's a question that was asked last week that got me thinking. And those of you that know me know how dangerous that is. We were asked, what happens if you make payments quarterly or annually, but the interest compounds monthly? So let's take a look. I know, I'm enjoying this a little too much. You know, student suffering is like cocaine to math teachers, right? Okay, so Pam invests $3,000 per year in an account that pays 9% compounded monthly. How much will Pam have after 20 years? So up until this point, we've said that the payment period has to equal the compounding period. Well, here the payment period is once a year. The compounding period is every month. We have to force those to line up. We cannot change the payment period. Pam is going to pay $3,000 each year. So what we have to adjust is the compounding period. 9% compounded monthly would be how much compounded annually? Well, the annual compounded rate is just an effective rate. So this is going to be an effective rate calculation. To do an effective rate calculation, does the amount of money matter? No, it doesn't.
You asked that question?
What's that?
What'd you say?
No, I don't think so.
No, the amount of money does not matter for the effective rate. So we can use whatever amount of money we want to here. We could use the $3,000, that's the annual payment, or we could just use whatever number. I'm going to use $10,000 just because it's a nice even number and it avoids some round off errors. So I want to find out how much that $10,000 will be at the end of 1 year at 9% compounded monthly. So it is $10,000 times, in our parentheses, 1 plus 0.09 divided by 12, and then to the power of 12. That's 12 periods in a year. Let me know when you guys get there. So 10,938.07 is your what you have at the end of a year. How much of that is interest? There we go. If you subtract the original $10,000, that's $938.07 in interest. So the effective rate over that year is 938.07 equals 10,000 times the effective rate times 1 because it was 1 year. So I'm just going to divide by 10,000 here. Which is going to give us 0.09387 equals our rate. Moving the decimal point 2 spots gives me 9.3807%. So we're going to round that to just 9.38% is the effective rate. So what this is saying is 9.38% is the effective rate between payments. So instead of using the 9%, we're going to use the 9% compounded monthly. We're going to use 9.38% compounded annually. They're equivalent. So Pam pays $3,000 per year for 20 years. So $3,000. Now we're back to an annuity calculation. 1 plus, for our rate, we're going to be 0.0938 divided by 1, because it's only once a year, to the power of 20, because we're in 20 years, right? Then minus 1, close parentheses, divided by, open parentheses, 0.0938 divided by 12. Close and close. Why is it 12? I don't know. It should be 1. You're correct. There we go. Sorry about that. I got 12 on the brain for some reason. That's why I messed up on that other one too. So 3,000 times 1, 2, 3 1 plus 0.0938 power of 20 minus 1 close divided by 0.0938. At 160,183.17. So you have to find that equivalent rate for that period of time is what you have to do. Now, what if the interest was compounded monthly and you were paying in quarterly? It would be the same type of thing. Let's say Carl pays $1,000 per quarter into an 8% compounded monthly account. How much will he have after, oh, let's go 10 years. So again, we have to find the effective rate, but now Carl's paying in every quarter instead of every year. So we're going to find the effective rate for 3 months. Effective rate for 1 quarter or 3 months. So again, we can pick whatever dollar amount for this effective rate we want to. I like to use $10,000. It's going to be 1 plus 0.08 divided by 12, because it is compounded monthly. But we're going to the power of 3, because we're only doing this for 3 months. So 10,201.34. Let me know when you get there. Looks like we got a handful of you there. So now how much of that is interest? Perfect. We subtract the $10,000 of principal, get 201.34 in interest. So now we figure that out using I equals PRT. So it's 201.34 equals 10,000 times our rate, but we do have to have a time in here. It's not just 1, it's 3/12, or 3 months. Could use 1/4 for 1 quarter if you wanted to there. So, first thing we have to do here is combine the 10,000 with the 3/12, which is 2,500. What's next? Divide by the 2,500. So 201.34 divided by 2,500. So 0.080536. What you need there?
Gonna be on the test, is it?
This would be an extra credit question.
Oh,
So I move that decimal point over to make it 8.0536%. This could be rounded, I suppose, 8.05 or 8.054. Because this is not a real good round-off, I'd probably go 8.054 as my percent. So then I would use my annuity formula using that. So Carl's putting in 1,000 per quarter for 10 years. So 1,000 times 1 plus, it's going to be 0.08054 per quarter. So it's going to be divided by 4. 10 years per quarter, so to the power of 40, minus 1, close our parentheses, divide, open, our rate of 0.08054, divided by, and it is still quarterly, 4, so close and close. Let me know when you get there.
Yep.
60,579.07.
Yes.
Okay. So you can see it can be done. It's just a little more complicated. Okay. So now what I want to do for the last hour and 20 minutes or so tonight is I want to do some review for this test. I did this a little bit before, the beginning of the class last week, but the toughest part of this test is remembering what type of interest to do, or figuring out what type of interest to do on the problem. So we're going to do some review, and actually I am going to save this